Today we are reviewing some more things from pre-calculus. All of what we're doing today is a review from what we did in pre-calculus. We're going to start with the definition of derivative, and then we're going to do average rate of change, differentiability, and we'll end today with the power rule for derivatives. So I'd like to develop the definition of derivative. So derivative means the slope of the tangent line. I would like to get the slope of the tangent line right here. I want that slope of I want the slope of that line. To get there, I'm going to begin with the line between these 2 points right here. Sorry, clearing my throat. All right. I have the secant line. A secant line is a line through 2 points on a curve. A tangent line goes through 1 point on that curve, right? So I want the slope of that line. And I know back from Algebra 1, the slope of this line is the change in y over the change in x, right? So that would be like y2 minus y1 over x2 minus x1. But our function, we're going to name this function f. So I'm going to call this function f of x. So change in y would be change in f. So this is f at x2 minus f at x1 divided by x2 minus x1, which I'm going to keep writing as change in x delta x. That's a little Greek letter delta that means change. Okay? Now, I would like to write this in the terms of the fewest number of letters that I can write. So instead of writing x2, you agree that change in x is x2 minus x1, right? Change in x is x2 minus x1. Another way to write that would be x1 plus change in x would be x2. So I'm going to replace x2 with x plus change in x. That way, x sub 1 I should write. X sub 1 plus change in x. So this will be f of x sub 1 plus change in x minus that f of x sub 1 all over change in x. Now I went from 3 different x components to only 2 different x components. Okay? Now, so that is still just the slope of the secant line. I still want the slope of the tangent line. So I'm going to move this point closer and closer and closer and closer and closer to that point. And as we do that, you can imagine what the secant line would do. It would get very, 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 I want to get very, very, very close. So I'm going to move x sub 2 closer and closer and closer and closer and closer and closer to x sub 1 so that it is infinitely close to x sub 1. It is so close that the difference is imperceptible. Okay? That means we're taking a limit. We are letting this change in x go to 0. So this is a limit. As change in x goes to 0 of the slope of that line. Here it's the slope of the secant line, but after we perform this limit, it will be the slope of the tangent line. As I'm going to write this down here in the box, but as I do it, I'm just going to remove the subscript on that x so that this is just any x right here. So that's going to be f of x plus change in x minus f of x all over change in x. And that is the definition of the derivative of f for any value of x. Okay? That is a beautiful, beautiful definition. However, writing the delta x's gets a little bit tedious when you're writing it over and over and over again. So by convention, we will often see an h. In place of the delta x's, we will see an h. But I need you to remember that h means change in x. Okay? It's easy to know it when there's this notation with change in x. But if you see an h there, I need you to think that is change in x. Okay? All right, now we have the alternative definition of derivative. This one is only valid at a single value of x. Not for any value of x, but for a single value of x. We're going to develop it very similarly. I'm going to begin by drawing that secant line. We would like to get over here to the tangent line, but we're going to start with the secant line. Okay? We know that our slope is change in y over change in x, which is f. We're going to call this f of x again. That's f of this value minus f of this value. I'm going to write that just like that. F of x minus f of a over x minus a. And I'm going to leave it just like that. Change in y, change in x. And now once again, I'm going to let this value get closer and closer and closer and closer, infinitesimally close to a. That means we're getting a limit here. We have the limit as x approaches a, whatever that number is. X approaches a of the slope. So f of x minus f of a all over x minus a. That is your alternative definition of derivative. Okay? All right. It is only valid at a single value of x. This one is good for any value of x. All right. Notation for derivative. This is Leibniz's notation. This is Lagrange's notation. This dy over dx is very useful for some things that we're going to be doing. When you see dy, I need you to think just a little bitty piece of y. This is an itty bitty piece of y. Okay? So this dx is an itty bitty tiny little piece of x. When you see dy, I need you to think that's a small little piece of y. Dx, a small little piece of x. Okay? Alrighty. AP is not going to ask you FRQs with the definition of derivative. Instead, they will test if you know it by multiple choice questions, like these next couple. If f of x is 2x cubed, then what is f prime at 2? And I look at my choices and they all have h's. And if they have h's, I know they're asking me a question about the definition of derivative. So I'm going to write the definition of derivative. F prime of x is equal to the limit as, and they're using h's, so I'm going to use h's, h goes to 0 of f of x plus h minus f of x all over h. Now I'm going to plug in this function. H is going to 0. F of x plus h. I am replacing x with x plus h. Replace x with x plus h. Minus f of x. Okay? I know that this is true. Now they want me to replace x with 2. So I will. I'm going to replace x with 2. 2 cubed is 8 times 2 is 16. Oh, I shouldn't write an equal to sign here. This is equal to f prime of 2. Okay? This is not equal to that. It's equal to f prime of 2. Okay. So which is the same? Let's see. This is no. This is no. I need the 16, so my answer is C. All right. Number 2. G prime of e squared. G is ln of x. What is g prime of e squared? Okay, I look at my choices. There's no h's, there's no delta x's, but there is a limit. So I know they're asking me a question about the alternative definition of derivative. So I'm going to write it down. Okay, so g prime at a, I'm just going to write it with a's first, is the limit as x approaches a of f of x, I should say g of x minus g of a all over x minus a. That's g prime of a. So I'm going to replace it with what I know needs to be there. Okay, a is e squared. So immediately I get the limit as x approaches e squared. Now I need g of x. Well, what is g of x? ln of x. Minus g of a. What is g of a? What is, find a little blank space, I really crammed things in here. What is ln of e squared? Well, ln of e squared is 2 ln of e, because we can move that exponent to the coefficient. That's one of our log properties. And ln of e is 1, so this is just 2. ln of e squared is 2. All over x minus a, x minus e squared. So I just need to find the one that matches that, and it is A. Okay, so that's how you'll be asked if you know the definition of derivative. Okay? Alrighty. Meanings of derivative. Slope of the tangent line. And instantaneous rate of change. Those are the meanings of derivative, okay? By the way, instantaneous rate of change is often abbreviated to just rate of change. If they say rate of change, if they ask you to find the rate of change, they are talking instant rate of change. They are talking derivative, okay? If they wanted average rate of change, that is different, and they will say average rate of change, okay? Also, a function is differentiable if its derivative exists. Okay? That's the meaning of differentiability. So a function is differentiable if its derivative exists. Okay. Average rate of change, instantaneous rate of change. AROC, IROC. Change in y over change in x, itty bitty y over itty bitty x. Okay? Number 3. Let f be a differentiable function with selected values given in the table on the right. What is the average rate of change of f? Average rate of change of f. That is change in f over change in x. On the interval 0 to 10. So f of 10 minus f of 0 over 10 minus 0. And now I'm going to go to the table to get these values. F of 10 is negative 20. F of 0 is 5. That's negative 25 over 10, which is negative 5 over 2. B. Okay, little average rate of change question. That's always on the AP exam, you guys. Average rate of change. All right. Now, a function is differentiable if its derivative exists. So what could make a function not differentiable? There are three things. A discontinuity, any kind of discontinuity, jump, hole, vertical asymptote, okay? Not differentiable, which means if a function is differentiable, it must be continuous, okay? Vertical tangent line, these are harder to see, okay? For instance, this is the graph of y is equal to the cube root of x. I just got rid of the axes. Right here, there's a vertical tangent line. Okay? The last is a corner or a cusp. My students usually like the word cusp. A corner happens when the slope of the function to the left of a is not equal to the slope of the function on the right of a. Okay? So right here is a corner or a cusp. Right here is a corner or a cusp. Okay? You can think of it as a sharp turn, but it doesn't have to be a super sharp turn. As long as the slope on the left is not equal to the slope on the right, you've got a cusp. So I could draw like, let's say it's a little piecewise function or something. So there's the piece on the left, and all I have to do is do a really slight little turn here, just a slight little turn. That does not look like a cusp, but it is. That's a cusp. Slope on the left is not equal to the slope on the right. Okay? Alrighty. You won't have to decipher something as slight as that. Okay? If I give you the graph, you're going to know that there's a cusp if there's a cusp. Alright? Okay, number 4. Let f be the function given by f is equal to the absolute value of x. Which of the following statements about f are true? We know what the graph of this looks like, don't we? Got this little v going on, yeah? Is f continuous at x equals 0? Yes, it is. True. Is f differentiable at x equals 0? No, it is not. We've got a cusp. Is f defined at x equals 0? Sure it is. F of 0 is 0. If I put in 0 for x, I get a number. So yes, it's defined. Okay? So we want it to be true. 1 and 3 are true. C is my answer. Number 5. Let G be the function consisting of 3 line segments, a quarter of a circle, and a semicircle, whose graph is given on the right. On which of the following intervals, these are intervals not points, on which of the following intervals is G continuous but not differentiable? Continuous but not differentiable. So immediately I see this discontinuity and this discontinuity. Okay? So from -4 to 9, from -4 to 9, G is not continuous. What about from -2 to 3? From -2 to 3. Is G continuous? Yes, it is. Is G differentiable? No, it is not. We've got a vertical tangent line right here. If we drew the tangent line, it would be vertical. So not differentiable from -2 to 3. It is continuous, but not differentiable. So this is true, but it says only. So is there any other spot where G is continuous and not differentiable? 3 to 7. From 3 to 7. And these are open intervals, so it never reaches 7. From 3 to 7. Is it continuous? Sure it is. Is it differentiable? No, it is not, because we have a cusp, or a corner when x is 5. So this is true, but again it says only. Negative 2 to 7. Negative 2 to 7. Continuous, not differentiable. That is true. D. Okay, so a few little multiple choice questions on that. Alrighty. Now we are at the power rule for derivatives. Power rule for derivatives. This is a pattern that our founders of calculus, Leibniz and Newton, found when they were using the definition of derivative. Okay, just a pattern that they observed. Calculus is a lot about patterns. They found that when you have x to a number, think of n for number, x to a number, then the derivative is, you take that power, you multiply it to the front, keep your x, decrease your power by 1. They found that to be the pattern. Okay? You can only use it if your exponent is a number. If your exponent is a variable, this does not work. Okay? Alright, so let's find the instantaneous rate of change of f. That's your derivative, itty bitty y over itty bitty x. Instantaneous rate of change of f. So, I'm going to use my notation f prime. Little power rule here. 2 times the front. Keep your x, decrease your power by 1. It would be a 1 power. I'm not going to write a 1 as a power. This power is a 1. Multiply it to the front. We get a 3. Keep your x, decrease your power by 1, but 1 minus 1 is 0, and x to the 0 is 1, so this is just a 3. The derivative of 3x is 3. The derivative of any constant is 0. You might want to write that down. The derivative of any constant is 0. So this is just our derivative. There's no need to box it. That's our derivative. Okay? Find the slope of the tangent line. That's our derivative again. Okay? I like to give you different meanings so that you can learn the different meanings of the derivative. Okay? And here's g. Well, this is not in a form, this is not in the form that we can use the power rule yet. We must change this to force it to be in a form where we can use the power rule. I'm going to leave the 4, don't move the 4, bring the x to the top, and give it a negative power. Okay? This is the same thing, but now it's in the form where we can use the power rule. So g prime of x is power times the coefficient. Negative 8 times the fourth is negative 2. Keep your x, decrease your power by 1. That's the derivative. Okay? Now, of course, they might write this in a multiple choice answer. They might write that as negative 2 over x to the 9. They might bring that x back to the bottom and give it a positive power. Or they might leave it like that. Be able to get there. Okay? If this was free response, you could stop right there and be fine. Okay? Number 8. Here's a messy y. What is the derivative? Okay, first, again, I need to rewrite this to make each term in this form. Each term must be in that form. So 1 over x cubed is x to the negative 3. The fourth root of x is x to the 1/4. 5 over 2x to the 30th is 5 halves x to the negative 30. Each time I'm writing x to a power next to it. Minus 7x to the negative 2 over 5. The root is always in the bottom of the power. So now we can write our derivative. I'm going to go piece by piece taking the derivative. Negative 3 times the front. Keep your x, decrease your power by 1. Power times the 3. That's 3 over 4. Keep your x, decrease your power by 1. Negative 3/4. Power times the front. Okay, a couple ways we could do this. 5 times 30 is 150, divided by 2 is 75, or 2 goes into 30 15 times, 15 times 5 is 75. Either way, we get a coefficient of negative 75. Keep your x, decrease your power by 1. Negative 2/5 times negative 7 is positive 14 over 5. Keep your x, decrease your power by 1. Carefully subtract those fractions. And then this would be your answer. And if you had to, you could write it in another form. Number 9. Okay, we have another messy h. This definitely is not in this form. So we must get it in that form. Okay, when you see an equation like this, when you see a single term denominator, STD, single term denominator, I want you to immediately get rid of it. Okay? Get rid of it immediately by doing a quickie divide. Take every term on top divided by that STD. All right? So h is going to equal 2x to the 4th over x squared. That'll be 2x squared. The x is reduced. Negative 3x cubed over x squared. Negative 3x. 9x squared over x squared. Negative 7x over x squared would be negative 7 over x, but I don't want x in the denominator because I'm about to take the derivative. So I'm going to write that as negative 7x to the negative 1. 1 over x squared. I don't want to leave it like that because I'm taking the derivative. I need to move x to the top given a negative power. So x to the negative 2. Okay? Now we take the derivative of each piece. Power times the front. Decrease your power by 1. The derivative of negative 3x, negative 3. The derivative of 9 is 0. The derivative of negative 7x to the negative first, negative 1 times negative 7 is 7. X to the, decrease your power by 1. Negative 2 times the front, keep your x, decrease your power by 1. This would be a safe stop spot. You just stop right there if it's an FRQ. If it's a multiple choice, here's what I usually do for the sake of your notes. I usually box my safe stop spot. And then I will write what could be a multiple choice answer. The multiple choice answer. Another little thunderstorm coming up here. I don't know if you can hear that thunder. Okay. This could be the multiple choice answer. Or they could get a common denominator of x cubed. And if they did, this would be 4x to the 4th, right? 4x is the same as 4x to the 4th over x cubed. This would be negative 3x cubed, because negative 3x cubed over x cubed is negative 3. This one would be 7x, and this would just be a minus 2. So one of those could be the multiple choice answer. Okay? All right, last thing for today, let's review our derivatives of the trig functions. The derivative of sine of x is cosine of x. Okay, we have to memorize that. Anything with a star you have to memorize. Okay, the derivative of cosine of x, negative sine of x. Okay, derivative of tangent x. Remember, tangent loves secant. Tangent always is with secant. Tangent loves secant so much it wants two of them. So secant squared x. You can think of it like that, or if you prefer, you could think of it as secant x squared. Either way is fine. Okay? Which means the derivative of cotangent x is negative cosecant squared x. The derivative of secant. Well, secant loves tangent. They always go together, so I know there's going to be a tangent here. But secant, tangent likes secant so much that it wants two of them. Secant, not the case. Secant is self-centered, and it needs to come in here too. I always say secant is self-centered. She goes first. But it's a product, so it doesn't have to go first. Secant x, tangent x. Don't forget your x's. Don't forget your arguments. Okay? Which means the derivative of cosecant x is negative cosecant x cotangent x. We must know those. We must know those. Because it won't be too terribly long and we're going to have to go backwards. You have to know these. Alright? Number 10, find the slope of the tangent line. That's the derivative of y here. Okay? When x is pi over 6. Alrighty. Well, the first thing I'm going to do is rewrite y slightly. I'm going to rewrite y as 1/4 sine of x. I'm just pulling that denominator out to the front. The denominator is just a number, so I'm pulling it to the front. If it was not a number, we would need to use the quotient rule, and that's coming up tomorrow. Cotangent x over 2 is 1/2 cotangent x. Now I'm going to find the derivative. Okay. The 1/4 just gets multiplied by the derivative of sine, and the derivative of sine is cosine of x. Don't forget your x's. The derivative, okay, the 1/2 just gets multiplied by the derivative of cotangent, but the derivative of cotangent is negative, so negative cosecant squared x. Now I am plugging in pi over 6 for x. And I'm writing what I'm doing. The dy dx at x equals pi over 6. You don't want to put an equal to sign here because this is not going to equal that with pi over 6 plugged in for x. So you want a new dy dx at x is equal to pi over 6 is equal to 1/4 cosine pi over 6 minus 1/2 cosecant pi over 6 squared. Okay. Believe it or not, this is a safe stop spot. A safe stop spot is, I don't have a little scientific calculator, anything that can be plugged into a scientific calculator, not a graphing calculator, a scientific calculator. And scientific calculators can do all the trig functions. So this is a safe stop spot. If this was an FRQ, you would stop right there and walk away. You would not do any further. However, these will be multiple choice questions usually. So I'm going to go ahead and change this to what you would have if it was a multiple choice question. Cosine of pi over 6 is square root 3 over 2. Cosecant of pi over 6 is the flip of sine of pi over 6. Sine of pi over 6 is a half. The flip of a half is 2. So cosecant of pi over 6 is 2. Which makes this the square root of 3 over 8 minus 2. That could be the multiple choice answer, or they could get a common denominator. Square root of 3 stays square root of 3 minus 16. 16 over 8 is 2. That's probably what they would put as a multiple choice answer. But I have seen them do things like this as well. Okay, big day for us today. We did the definition of derivative. We did differentiability. We did the power rule for derivatives. And we reviewed AROC, average rate of change.